We're going to look at many different applications of the limit throughout the semester, actually, even though later in the semester it won't feel like that. But one of the applications of the limit is going to be to find what we call the area under a curve. And a large goal in calculus is finding what's known as the area under a curve. So what do we mean by that? Well, we have a function here. We're going to mark off an interval on the x-axis. Let's call it a to b. And what we want to do in calculus is find the area between a function. We're going to assume, for now at least, that these functions are above the x-axis, just for convenience. But a function above the x-axis, mark off an interval a to b. We want to find the area between the function and the x-axis on that interval a to b. Now, how are we going to find that? Well, we're first going to approximate that area. To find this, we'll first approximate the area. There are several different approximations that you could use, which you can then extend using limits into finding the exact area. We're going to look at two sets of rectangles we could use to approximate this area. And then, if we are careful with our approximation, we can extend that to finding the exact area using a limit. So meaning, in the limit, our approximation is going to become an exact area. A little more on this in a moment. There's also a video or might be a small thing I lifted from a Wikipedia page showing what this looks like. But we'll talk about how the approximation leads to the exact area a little later in this video. For now, let's just discuss the approximation. We're going to approximate the area using rectangles. Now, which rectangles? How are we going to find them? Well, to illustrate the approximation, here we're going to use 4 rectangles for this first illustration. We're going to use 4 rectangles. And what we're going to do is take this interval, a to b. I should have been a little more careful in filling in that area. We're going to take that interval, a to b. We're going to divide it into 4 subintervals of equal length. The of equal length will make the algebra more convenient. Divide the interval into 4 subintervals. These 4 subintervals are going to form the bases of the rectangles. We are going to approximate the area using rectangles. We're going to want to find area of a rectangle. Area of a rectangle is, well, it's the one side times the other side. Divide a to b into 4 subintervals. Those will form the bases. So from that, we have one of the sides of the rectangle we need to find the area of the rectangles. Now, the heights of the rectangles will be determined using the endpoints of these subintervals. Well, we're going to use the endpoints of these subintervals. Now, what does that look like? Well, I'll illustrate that in a moment, but we're going to see in a moment as well that this construction leads to 2 possible choices because, a subinterval, if you take an interval a to b like this, you divide it up into pieces. You use each of these 4 pieces to form a rectangle. We're going to use the endpoints to form a rectangle. Well, on this piece here, you could choose this endpoint. You could choose this endpoint. So this construction leads to 2 possible approximations. So what do they look like? Over here, we'll illustrate the 2 possible sets of rectangles. So these are supposed to be that same function. We have the interval a to b. What are we going to do? We're going to use 4 rectangles because that's part of this construction. Actually, this should really be a 4th bullet point under that. Divide a to b into 4 subintervals of equal length. 4 is convenient because you could just divide it in half, divide it in half. So far, these aren't different. But, well, so far, we have the bases of the rectangles. So this right here forms one base. This right here forms another. This forms another. that forms another, and similarly over there. But the other side of each rectangle is determined using the endpoints of the subintervals. So we have two different endpoints we can choose. We can choose the one on the left, we can choose the one on the right for each subinterval. So over here, I'm going to choose the left endpoints. Now, what does that mean, I'm going to choose the left endpoints? Well, we're forming rectangles here. For all of this, I find it much easier if I'm always thinking about forming rectangles and in the computation, finding areas of rectangles. So right here, we have this subinterval between A and that first dash point thing. The one side of the rectangle is this piece of the x-axis. The other side is given by the function evaluated at, in this case, the left endpoint. The function evaluated at the left endpoint is that height. It's a y value corresponding to the point x equals a. So right there, that's going to form the height of the rectangle. And how are we going to draw this entire rectangle that we're finding the area of? We're going to take this y value, go over, and form a rectangle like that. And we're going to do that with all of these. So for our second subinterval, this piece between the first dash and the second one, go to the left endpoint. The height is determined by that y value. Form a rectangle like that. For this third subinterval, we have a left endpoint and a right endpoint. Here in this first one, we're choosing the left endpoints, which is over here. The height of the rectangle is determined by that left endpoint, and you go over like that. And for the fourth subinterval, since we're using 4 here, the left endpoint is still the one on the left. The other side of the rectangle is determined by the function evaluated there, and we get the other side of the rectangle. So right here, just going to shade these in, we have 4 rectangles. And we can find the areas of those rectangles in a moment. We'll do that when we have a specific function. But notice in this case that this approximation is an approximation, meaning it's not going to give us the exact area, because notice these triangular-like wedge pieces. They're not triangular because the top is curved. So maybe I should just say these wedge pieces are part of the area we wanted on the first board, but they're not part of our approximation. So right there we have one set of rectangles we could choose. There's another using right endpoints. For the first example of showing how the rectangles form, I went through each rectangle like that. There's another potentially faster way of showing the rectangle construction. And here's how I like to do it. And I'll illustrate it for the right endpoint choice. Mark off the points on the x-axis. Now it's divided into 4 pieces. And just draw a line, vertical line at each of those. So right here we're dividing the area into those 4 pieces. But we're going to we aren't yet going to be able to find those exact areas. We're just going to approximate them using rectangles. Now, what does it look like using right endpoints? Well, we still have the base of the rectangle, the first rectangle there, with left endpoint at A, right endpoint at whatever that value is. So the height of the first rectangle is going to be determined by the right endpoint. It's going to be given by that line. And we're going to use the right endpoint to approximate the area, and that will, the first strip of that area, we're going to approximate using the right endpoint. So notice here, in this case, that is an approximation because it's a little more than the exact area, but it's an area we can find because we can find areas of rectangles. And we're going to do that for these other 3 strips as well. Second strip, take the right endpoint. The height of the height of the second rectangle is given by the function value at that endpoint, given by that y value. So the second rectangle is formed like that. And similarly, the third one, use the right endpoint. There's the base. The right endpoint goes up here. this way this time. And for the fourth one, the right endpoint is at x equals b. The height is given by that line. And the rectangle is formed like that. So notice we do have two approximations. Let's define these two approximations. Well, before that, notice, you can view these as being formed, kind of like steps, if you want. For the left approximation, I do always like, starting on the left and going like that. For the right approximation, I actually like starting over here and going toward that way, but you can do whichever one you want. So let's define these. I like how I wrote it in my notes. So I'll do it like this. For this reason, we define two. I use the number 2 up there. So I'll use the number 2 down here. We define two approximations. L4, so 4 rectangles, capital L. L4 is the combined area of, so maybe I'll say definition. This is kind of an informal definition, but that's okay. L4 is the combined area of the rectangles found using the left endpoints meaning the left endpoints as defined over here. And definition for this, R4 is the combined area of the rectangles found using right endpoints. So same sentence, but with L instead of R, or R instead of L, so I scribbled it out. So we have now two different approximations, and notice again, these are approximations. These do not give us the exact area. But, let's make one more observation before doing some computations. So I'll say remark. Remark. So here we have 4 rectangles. But what happens in general? So let's say if we let n equal the number of rectangles. So we'll let n equal the number of rectangles. Well, if we let n equal the number of rectangles, you may not want to write what I'm about to write until I write the entire sentence, because I'm going to piece together something. If we let n equal the number of rectangles, well, then what are our approximations? Our approximations would then be ln, and our other approximation would be rn. Now, we can still find an approximation using n rectangles. It's still not going to be exact. But as we let that number of rectangles get large, as we let that number of rectangles go to infinity, these error pieces, whether they're errors beyond the exact area or errors below the exact area, as we let that number of rectangles keep going up and up, these error terms keep getting smaller. Meaning, as the number of rectangles gets large, these error pieces go away. The error goes to 0. which means as we let the number of rectangles get large, the approximation will become exact. The approximation will approach the exact area. And that's true regardless of which approximation we use. If we use right endpoints or left endpoints, in the limit, the area will become, well, in the limit, the approximation will become exact. And that's a pretty large theorem in math. So, theorem. Remark, if we let n be the number of rectangles, then we have this theorem. The limit, as n goes to infinity, of the left approximation equals the limit as n goes to infinity of the right approximation. And this meaning, this equality, gives, maybe I'll say equals, that's a good verb, and this equals the exact desired area. And that's a very important theorem in math. So for now, let's look at a couple computations of just the approximation, and then later we'll look at finding the exact area. So let's do 4 area approximations. Well, I'm actually going to do 8 area approximations, because for each one of these I'm going to do the left and the right. In anything submitted and graded, I'm not going to ask you to do both, since the computations are pretty similar. But for this, I will do both for each one of them. So approximate the area under the curve. It is noticed with our graph transformation, this function is above the x-axis. Approximate the area under the curve on the interval 1 to 3 using 4 rectangles, 2 rectangles, 8 rectangles, 3 rectangles. And yeah, I do have this in this order for a reason. I usually find, well, for this interval, 3 rectangles I think is the most difficult. So let's do 4 rectangles. So first I will find L4 and then I will find R4. So what does this look like first of all? Well, this curve looks a lot like the one we already drew. We have the interval 1 to 3. Maybe I'll make it a little bigger. We have the interval 1 to 3. There's the function. We want to approximate that area. We're going to use 4 rectangles. Let's divide it into 4 pieces. 4 equal pieces. Now, to do this, we're going to need these x values. So, dividing 1 to 3 into 4 pieces, well, the one right in the middle is going to be 2. The one between 1 and 2, is 1.5. Also known as 3 halves. Between 2 and 3 is 2.5, also known as 5 halves. In these computations, since I always think we need rectangles and areas of rectangles, I usually find that finding those x values is the easiest place to make a mistake. The rest is just a computation, and well, it could be argued that finding those x values is more important than the final computation. But first we're going to do our left approximation. What does that look like? Well, use the left endpoints. So what I'm going to do is draw the tops of the rectangles using the tops of the lines we already drew. So we need these 4 rectangles. Where am I going to write this? Let's do L4 here. L4. So first, notice the base of each rectangle is going to be 1/2. Now from 1 to 3 halves is 1/2. From 3 halves to 4 halves is a half. From 4 halves to 5 halves is a half. From 5 halves to 6 halves is a half. And I'm going to, well, I'll illustrate why that's important in the second line of the computation for this first one. But what's the area of this first rectangle? Well, what's the function? Actually, maybe I'll write it down here. No, I'll write it here. The area of the first one, the base is a half. What's the height of the function? Well, the height of the function is given by that y value. The y value corresponding to x equals 1. So for right now, I'm just going to write it like this. A half times f of 1. And I'm going to write it a little smaller. L4 equals a half times f of 1. The base is a half. The height is given by the function at the left endpoint. The next rectangle. The base is from 3/2 to 2, so the base is again 1/2. What's the height of the rectangle? The height of the rectangle is this y value. The y value corresponding to x equals 3/2. The y value corresponding to x equals 3/2 is f at 3/2. The third rectangle, this one, notice this is going to give us an under approximation of the exact area. I'll tell you now, we'll see later in the video, the exact area, I forget if it's 14/3 or 44/3. I think it's 14/3, or I think it's 44/3. This next one, so our answer will be less than that. We'll observe that later in the video. The next one, the base is again length a half. They're all going to be length a half by construction. And the other side is given by the function evaluated at, in this case, 2. It's the y value corresponding to x equals 2. And the fourth rectangle, the base is again a half. The height is given by the function evaluated at 5/2. The height is this y value here. Function evaluated at 5/2. So we just need to evaluate all of this. Now, before evaluating this, there is a convenience we can observe. All of these terms, there are 4 terms here, all of them have a 1/2. So we can factor out that 1/2. Factor out the 1/2, well then you have to add all those things together in the middle. But there is going to be less, multiplication by a half, seemingly. So we need now f at 1. I'm going to write these down here since I'm going to need them. F at 1, 1 squared plus 3 is 4. F at 3/2 is the next one we need. 3/2 squared plus 3. What's 3/2 squared? It's 9/4. 9/4 plus 12/4, 21/4. So I'm just going to write that here because I don't have much room. Next we need f at 2. F at 2, 2 squared plus 3, 7. We need f at 5/2. F at 5/2 equals what? 5/2 squared, so 25/4 plus 12/4, so 37/4. Why did I write them in that configuration? I don't know. F at 1 is 4. F at 3/2 is 21/4. F at 2 is 7. F at 5/2 is 37/4. So now we need to add these together. I'm going to add these together. I'm going to add the whole numbers and then add the fourths. 4 plus 7 is 11. 21 plus 37 is what? 58. 58 divided by 4. 29 divided by 2. And then what does this equal? Well, it equals what? 22/2 plus 29/2. So that's 51/2. 51 halves times that other half is 51 fourths. So we have 51 fourths. What is that? That's 12 3/4. So yeah, 44 thirds does sound right as the exact area, which we'll see later. But this is an under approximation. So right here we saw the left approximation. Let's look at now the right approximation, the right-hand approximation. And what does that look like? Well, I don't need to write A again. Let's draw what these rectangles look like. And in general, for these, you don't have to draw out the function if you don't want to. Once we get to part C, I'm not going to draw the function out. So here we have 1 to 3. We're still dividing it into 4 pieces. We have 2, we have 3 halves, we have 5 halves. But what do the right-hand endpoints look like? Well, what rectangles do the right-hand endpoints give us? They give us this one, they give us this one, they give us this one, they give us that one. And in your notes, it may be worth putting like a mark or something by that line after the factoring and comparing it to the one we're going to get for the right-hand approximation. But I need to erase it. So I am going to refer back to this line while we're doing the right-hand approximation. So what does the right-hand approximation give? Well, I'm still going to start on this first rectangle over here, even though I drew a line starting over that. First rectangle is this one. The bottom of the rectangle has length 1/2. The height of the rectangle, well, notice the height of the rectangle is no longer given by the function at 1. The height of the rectangle is given by this line, which is the function at 3 halves. The second rectangle, which is, this one, the base is still going to be 1/2, but again, the height of the function is given by this line. Line segment, I suppose you could say. But this line over here is given by the function evaluated at 2. We're using right endpoints now. Right-hand endpoints. The third rectangle is given, well, the base is still 1/2. The height is given by this line, the function evaluated at its right endpoint, 5 halves. So 1/2 times f at 5 halves. And then the fourth rectangle, I guess I should shade this in. I've been shading them in. The fourth rectangle, the base is still this thing, 1/2, and the height is given by this line segment, the function evaluated at 3. And right here, now if you just look at this equation before we factor out the 1/2, we have 4 things added together, and they're all one thing times another thing. Now the area of a rectangle is one thing times another thing. So we have rectangle plus rectangle plus rectangle plus rectangle. When doing any of these, I always, even when writing out this equation, notice for all of them, I went back to rectangles. I went back to, we need 2 sides of each rectangle. Now, area of a rectangle, we've known that for a while. So it's nice if a major part of thinking is we need 2 sides of a rectangle. Now what does this equal? Well, let's factor out a 1/2. And what are we left with? F at 3 halves, F at 2, F at 5 halves, F at 3. And before we evaluate this, well, notice we have F at 3 halves, F at 2, F at 5 halves written, so all we need to do is find F at 3. But compare this line to the left-hand approximation. The line that I put a star next to and said I'm going to refer back to. If you compare this to that, you'll notice they're very similar. they all have that half, but they all also have these three terms. And the only real difference is the right-hand approximation has a function at 3, whereas the left-hand has a function at 1 in this case. More on that in a moment. But we need f at 3, so I'm just going to fill in f at 3 here. F at 3, 3 squared is 9, plus 3 is 12. So what do we get? Well, we get a half times f at 3 halves. 21 fourths plus f at 2 plus f at 5 halves plus f at 3. And what does this equal? Well, again, I'm going to add whole numbers first. 7 and 12 make 19. 31 and 27 make 58. So do 21 and 37. They make 58 fourths, which divided into 2 gives you 29 halves. 19 is 38 halves. 38 plus 29 is 67. 67 halves times a half gives you 67 fourths. So this approximation gave us 67 fourths, which, I told you the exact area is 44 thirds, which is, 14 and 2/3. We should expect this to be an over-approximation more than the exact area, 14 and 2/3, and this is, it is, what is that, 16 and 3/4. And the first one was something else. What was it? It was 12 and something, which gave you an under-approximation, as we expected with our diagram. So let's now do part B with 2 rectangles. Why did I put that second? Well, the first things we talked about, we used 4 rectangles, so I figured let's do all 4 rectangles first. So now let's do 2 rectangles. Well, again, I'm going to draw the function for this one. Function looks like that. And again, I'm going to do both approximations. In your homeworks and tests, you don't have to do both. You can do only one if you want. We have 1 to 3, but this time we're dividing it into 2 pieces. So we divide it into 2. Well, the point immediately between 1 and 3 is 2. So I'm going to find L2 and R2. What's L2? Well, the base of the first rectangle, maybe I'll draw a rectangle. The left-hand rectangle is given by the left endpoint. The base has length 1. The height has height f of 1. So we get 1 times f at 1. And that first one doesn't really look right. The second rectangle here, the base is again 1. The height is f at 2. So plus 1 times f at 2. In this case, you could say, factor out 1 or something. I'm just going to say equals f at 1 plus f at 2. F at 1 is 4. F at 2 is 4 plus 3, which is 7. So our left-hand approximation here gives 11. And how about the right-hand approximation? Well, we still have 1 to 3. We're dividing that into 2 pieces, which puts the middle point at 2. But the right-hand approximation is going to give us these rectangles. First one, so R2. The one side is 1. The height is now given by this line, f at 2. The second one, the base is 1. The height is now given here by that line, f at 3. F at 3. So this equals f of 2 plus f of 3. F of 2 was 7, f of 3, 12. So that gives us 19. Now, well, first, again, comparing these answers to 14 2/3, this does give an under approximation as we expect. This does give an over approximation as we expect. And again, 14 2/3, we'll see where that comes from later. Now, just so you know, I'm not just coming up with that number by doing a computation. I've done this example a handful of times, the last few semesters. So, I know what the numbers are supposed to be. So let's do part C. Now, so first of all, for 8 rectangles, I'm not going to, for this one I'm just going to set it up because I'm not going to make you do 8 computations and deal with all those inconvenient numbers. That's, well, I'm not going to ask you that. But this one is to illustrate something. A couple things, actually. So I'm just going to say here, we set up 2 approximations. Now, well, let's form the rectangles. So first, how do I want to do this? I'll draw it out like that. Yeah, okay, I'll do it like this. So first, we're dividing this into 8 pieces. 8 is kind of a convenient number for our interval here, because we can keep dividing these in half. The one immediately in the middle is 2. The one immediately between 1 and 2 is 3 halves. The one immediately between 1 and 3 halves is 1 1/4, 5 quarters. And from here, you can actually count through these. 1 is 4 quarters, 4 quarters, 5 quarters, 6 quarters, 7 quarters, 8 quarters, 9 quarters, 10 quarters, and 11 quarters. Now, the numbers won't always work out that nicely where you can divide them in 2 and just take half of things. So, where do these x values actually come from? So let's do that here. So let's say to find x values, let's say algebraically. No, maybe I won't say 2, I'll say we find algebraically. We find the x values. How do we do that in this case for part C? Well, we have the interval 1 to 3. So we're going to take, well, we're dividing the interval 1 to 3 into 8 pieces. We're dividing an interval of length 2 into 8 pieces. So we're taking the length of the interval, 3 minus 1, and we're dividing that into 8 pieces. And that division is going to actually give us the length of the base of each rectangle. What is that here? 2/8, which is 1/4. Now, I probably should have put this on a different board. Well, whatever. Now, here's our x-axis. We have that 1/4. I'm going to mark off 1. I'm going to mark off 3, because that's the interval in question. And how can we use that 1/4 to find these values? Well, first I'm going to divide it into 8 pieces. So I'm going to put, 7 lines. How do we find those x values? Well, each subinterval has length 1/4. First x value is 1. So the second x value is 1 plus 1/4. 1 plus 1/4. What is that? Well, 4 quarters plus 1/4 gives us 5 quarters. What's the next one? Well, the next one is this x value plus another 1/4. 5 quarters plus 1/4. What is that? 6 quarters. Reduces to 3/2. And so on. And what's the next one? 6 quarters. Also known as 3/2, 6 quarters. Plus another 1/4. This is the length of each subinterval. So we can use this to count through our x values. We start at 1, we go over a quarter. So we have 1 plus a quarter. We go over another quarter. We go over another quarter. Maybe I'll actually write it like this. Maybe this will be more illustrative. 1 to 5 quarters. Plus another quarter gives you 6 quarters. Plus another quarter, 7 quarters. Plus another quarter, 8 quarters. Plus another quarter, 9 quarters. Plus another quarter, 10 quarters. Plus another quarter, 11 quarters. Plus a final quarter gets you to 3, which is 12 quarters. And then over here, we just reduce all those numbers. So either way you want to figure these out. For some of them, especially for one like 3, figuring them out, just by looking at them is kind of, well, it's doable, but it's certainly not like, finding immediately between 1 and 3 is 2. So for that one, I would recommend an argument like this. And for one like this, an argument like this is particularly helpful because you can really check yourself by observing down here. If you do write 1 as 4 quarters, and you leave everything unreduced, you can check yourself. 4 quarters, 5 quarters, 6 quarters, 7 quarters, 8 quarters, 9 quarters, 10 quarters, 11 quarters, 12 quarters. And in the reduced form, I believe I even said that, 4 quarters, 5 quarters, 6 quarters. So you can find them, visually. Some of them work out more conveniently than others, or you can find them algebraically by taking the length of the interval, which in this case is 3 minus 1, dividing it into 8. And this argument would work for the other ones as well, for 4 and 2. Now, how are we going to set up these approximations? Well, let's do it like this. Oh, well, once you have those, you form your strips of the area. And then how are we going to do the approximation? Well, L8. I'm going to, when we set this up, and here we set up, I am going to factor out the common term, which in this case is that 1/4. So how, if we go back to the example with 4 rectangles, and you look at those 2 lines that we compared. So in the first one, it was a half times f of 1 plus f of 3/2. It's f of 2 plus f of 5/2. For the other, it was a half times f of 3/2 plus f of 2 plus f of 5/2 plus f of 3. Here, we're going to use a similar argument, but we have to adjust it for these rectangles. What is the length of each rectangle? What is the length of each rectangle? Maybe I'll do it like this. No, I won't. Then I'll mention this. The length of each rectangle, the bottom piece, is always a quarter. So we have a quarter. Times what? Well, the height of the first rectangle is given by the left endpoint. So f at 1. The height of the second rectangle is given by the second left endpoint. So f of 5/4. The third one is given by the height of the third rectangle, or is given by the function at 3/4, or sorry, 3/2. And then we keep going on. 7/4 gives us that rectangle. F at 2 gives us that rectangle. F at 9/4 gives that one. F at 5/2 gives us that one. Until we get to the last one. Notice here, for the left-hand approximation, the last rectangle is determined by f at 11/4. And that would give us an approximation that looks like this. I guess I'm going to have to go on to like 2 lines. in your notes, it would be nice if you could write this all on one line, which I didn't here. And notice here, this does give us a rectangle. A quarter times f of 1. A quarter times f of 5 quarters, and so on. So we factor that out. How about the right-hand approximation? Well, to do that, I'm not going to allude to this diagram. I'm going to simplify the diagram. Because notice in this, the actual function doesn't matter too much. Well, for setting it up, it doesn't really matter at all. As long as it's continuous. But, what can we do? Let's do it like this. 1, 3. 1 and 3. So we have, what, 5 quarters, 3 halves, 7 quarters, 2, 9 quarters, 10 quarters, 5 halves, 11 quarters. I wrote 7 instead of 11. 11 quarters, and 3. Which of those values did we use for our left-hand approximation? We used 1. We used f at 1. We used f at 5 quarters. We used f at 3 halves. We used f at 7 quarters. For the left-hand approximation, we used f at 2. We used all the right endpoints, the left-hand endpoints for each subinterval. So we used all of those for the left-hand approximation. The right-hand approximation, if you compare this to the two equations for the 4 rectangle case, the right-hand approximation uses the right endpoints. And I'm going to circle those with large circles. So the right endpoints for each subinterval are given by those large circles. The left endpoints for each subinterval are given by the filled-in circle. So I'm going to, before even filling in the right-hand approximation, I'm going to write down what I just said to make this diagram more clear. I'll write it here. I'll just say each x value with a filled-in dot is used for the left-hand approximation, and each x value with a large circle is used for the right-hand approximation, which is a large word, so you can just write that in PPROX. And it may be useful to also do this diagram for the 4 rectangle case and compare it to those two equations. But what do we get here? Well, we're still finding areas of rectangles. The bases of the rectangles are still a quarter, but here we're using the right-hand endpoint. So we're going to start with the open circle at 5 quarters. So times f of 5 quarters plus f of the next thing, 3 halves, plus f at 7 quarters, plus f at 2, plus f at 9 quarters, plus f at 5 halves, plus f at 11 quarters, and then we include the last one, because we're using right endpoints, plus f at 3. And I would never ask you to actually find, what this simplifies to. 4 is probably the most I would ever ask. But, if I say to just set them up, which I may, you can stop at this stage. So do notice the similarities between the two. The only real difference is which endpoint of the original interval is included. So yeah, I know I didn't completely follow the directions here, but that was intentional. You don't have to worry about being asked to simplify that for 8 of them. It's to illustrate that shortcut for finding the approximations, and we're going to use that shortcut for part D. So for part D, I'm not even going to draw the function. I'm just going to find the x-axis subintervals. We're still on, because I was doing it like this, we're still on 1 to 3. But in this case, we're dividing it into 3 pieces. What are those x values? Well, how do we find them? We have an interval of length 2, 3 minus 1, and we're dividing that into 3 pieces for part D. 3 minus 1 is 2, 2 divided by 3 is 2/3. So each of these subintervals is length 2/3. One plus 2/3, 1 plus 2/3, 3/3 plus 2/3, 5/3. 5/3 plus 2/3, 5/3 plus 2/3, 7/3. 7/3 plus 2/3 is 9/3. And again, you can count through these because you have 3/3, 5/3, 7/3, 9/3. It follows, an arithmetic progression. So now we want L3 and we want R3. So again, we're forming rectangles. When drawing the function, it's much easier to not make the mistake I'm about to illustrate. When just doing the interval, it's easy to make the mistake I'm about to illustrate. What are we using for the left-hand approximation? We're using this one, using that one, and we're using that one. So it's very tempting to go to f of 1 plus, it's very tempting to go to f of 1 plus f of 5/3 plus f of 7/3, just from this diagram. But that does not give us our rectangles. The rectangle, those give us the heights of our rectangles. We still need to multiply them by their bases. And the base here has length 2/3. So we have 2/3 times all of that. Then what does this equal? Well, this one's a little bit inconvenient of computation. But that's okay, I guess. F at 1 is 4. Well, that wasn't inconvenient. What's f at 5/3? F at 5/3 is 25/9 plus 3. I'm just going to write it like that. F at 7/3 is 49/9 plus 3. And now I'm going to combine the whole numbers. Don't forget the 2/3. 4 plus 3 plus 3 is 10. 25 plus 49 is what? 74. So you get 10 plus 74/9. 10 is what? 90/9. 90 plus 74, 164. That's a bad looking 6. It was 164. 9. 2 times 164. 328. 3 times 9, 27. And now let's do the right-hand approximation. R3, we're doing rectangles. The base of the rectangle is again 2/3. But here, we use the right endpoints. those three. So we use f at 5/3 plus f at 7/3 plus f at 3. So we have 2/3. F at 5/3 was 25/9 plus 3. F at 7/3 was 49/9 plus 3. F at 3 was 12. Yeah, 12. So we have 2/3. 12 plus 3 plus 3 is 18. 25 and 49 again make 74. 9. So what does this equal? It equals 2/3 times what? 18 is what, 162, I guess. Oh, 2/3. No, 236. So 162 plus 74/9 gives you, 236/9. And 236 times 2 is what? 472. All over 27. So these computations are pretty important, but it's particularly important to see how those two equations differ. So before looking at the exact area, let's make one more observation. In all of the examples we've seen so far, the left-hand approximation gave an under-approximation, and the right-hand approximation gave an over-approximation of the exact area. But that's not always the case, as this example shows. In this example, L3, so the left-hand approximation of 3 rectangles, is going to give an over-approximation, and R3 will give an under-approximation. Now, why is that? Well, let's mark off, an A and a B. What does L3 look like? Well, let's take 3 rectangles. What does L3 look like? It's determined by left endpoints. Determined by left endpoints. Left endpoints. So here, L3 looks like this. Notice L3, I should probably center that. Notice here, L3, the rectangles go more than the area, the exact area. And here, R3 is going to give an under approximation. Now why is that? Well, let's just draw it out as a lousy line. What does R3 look like? Well, we use right endpoints. So R3 looks like this. And notice we have these wedge-like things that don't contribute, or that aren't included in the right-hand approximation, R3, but are part of the area. So I originally was going to show next how we can do a computation that gives the exact area. But doing that would take about 20 minutes, maybe even a little more. And right now I'm pretty close to an hour as it is. So I'll stop this one here and do the exact area computation another time. Later this semester, in I believe week 5, we are going to go back to this exact area. I think it's week 5, I think it's Wednesday of week 5. We are going to go back to this exact area. So for now, I'd like you to try the computations, but also it's very important on Canvas in the week 2 module, there's going to be, there is something posted which brings you to a link. Well, there's a link posted which brings you to a page that will show you how more rectangles leads to the approximation becoming exact. It'll show you how these error terms with more rectangles go away as you use more rectangles. So definitely And I think I'm a little under an hour here. So definitely, use that link and look at it. And, that visual is among the more important things you cover in a calculus class. So do practice these approximations and setting them up, especially with the thing, with the dots like this. It's nice to get used to, something like that where, you don't have to draw out the entire function. You can just, reduce the computation to looking at the x-axis. So do practice that and definitely look at the link.